Now, let's consider the same problem where I am out over here and I call this thing as the CC1 building, where this is me who is thinking that after the lecture, how do I go out and let us say withdraw some money from the ATMs. Good news, ATMs are still working around over here. And that's what is the ATM machine. So this is where I need to go. And this will of course have a very specific name. This is what I want to do. And that's what it's called as the goal. And of course, if you are aware of it, what really happens around over here, we've got some beautiful roads around. We've got some beautiful pavements that I could use. We have got interesting buildings onto the way. So how do I model this problem? The first and foremost job that explains 90% of the difficulty where people get into is to define something called as a state. So, we're looking at computer programs. From your point of view, you may see a physical, beautiful world which has so many atoms, which has so many molecules, which has so many things which have a special name, the trees, the roads. But my environment, for the sake of problem solving, needs to be encoded. So I need to be able to encode my environment into a digital format, which could be stored as a set of real numbers, strings, booleans, characters, you name it, it's up to you. As long as everything is in a nice digital format, so that I can do some programming about it. Now, what really happens is that as I try to go from my current position, also called as a source, all the way up to where I want to go, also called as the goal, the environment is not going to remain the same because at least I am the one who will be moving. So my head will go zoom, zoom, zoom as I walk along. It's a change. My hands will go nice, up, left, right. My feet will be walking. I look at things around. My head will move. And therefore, any encoding of the environment will change along with time. And remember, our assumption is that the environment is completely static. So when I say things will change around, who is causing the change? It's me. As an agent, I'm doing some changes for purpose. And me doing some changes on purpose is changing a part of the environment. It's changing my encoding, or it's changing, as we say, the state of the system. The state of the system continuously changes as I do all these things simultaneously. I move, my location keeps on changing. So let's start off with the ambitious definition that anything which in the environment, because of my motion, because of my actions, because of my decisions and implementation of those, will change as I make this beautiful transition from the source to the goal is what I'll encode as the state, and therefore let me write down what should be my state variables for this part of the problem. So the way you could visualize this problem is, of course, by a much fancier diagram. I cannot draw it into 3D, so let's draw it somehow into the 2D. So that's CC1, and this is where the ATM is located, and there are beautiful things around like the trees. I have a bad drawing, the roads, the buildings, and so on. So what changes as I go along from CC1 to the ATM? Let's list a few of them. Now, if you can look at the little window outside, you will see that the lighting will change. From evening, it's becoming night. The lighting will change. The trees will shake, so their position will change. What else will change? I'll have vehicles moving. Their position, orientation, everything will change. What else will change? My head position will change. I will start blinking. My eyelid position will change. So you can see if I really need to encode this, too many variables, plus the environment is not static itself because I don't control all these things up. And therefore let us look at the entire problem once more, because I could not even list down a problem in a way that has my own assumptions. Trees shake. Do they matter me? No. They shake a few millimeters. I abstract it out. I say details not required. Vehicles moving. Okay, when the vehicle comes, I'll do something. I'll take a left, I'll take a right. I mostly use a pavement. And barely do I need to care about moving vehicles unless I'm in an intersection, in which case I wait for some times. That's all. It's reflexive in me. I won't care about it now. When it comes, I'll see what needs to be done. So I again abstract this out. That's the most terrible. Lights. Does it affect my decision? Well, no. Even if it's morning, I'll take the same route. Even if it's night, I'll take the route. So that's irrelevant. Oops. That's a completely irrelevant detail. I absolutely don't need that. I mean, next what? Some bacteria will move. Does it affect my decision? No. That's an irrelevant detail. So after slashing out everything, all that I left is my own position changes. Now again, eyelid. Do I need to really control it? Take an action? No, just abstract out. Head position. Why will I just look around? Is that even a part of the plan? Is that even important? No, again, abstract out. And therefore you see, most of the details are getting abstracted out, which means I could more practically try to encode what my state is. So what really affects my motion, and I need to control it. I cannot do anything about it. So the way that I walk is by a motion of my hip joint. So I move my hips, I move my knees, and After I move all these things, I move my angle. All this together creates a motion, and because of those motion I move, and therefore my own position in terms of x, y, z and my own orientation that changes. So much more realistic. Now again you'll say that, do I need to consider all the hip joint, knee joint, ankle joint? That's the backbone of my motion. What is really you walking around? It's you lifting your ankle, getting the ankle back in, lifting the other ankle, then your knee and hip also moves as a result of all this. That's walking. That's how my actions are defined. So I cannot really say that I'll leave it out. It's important. But do I really have to consider my motion at that level of detail? If you need to move, all that you say is that let's move forward. You don't say that let's lift up the left ankle by 30 degrees, let's swing the right angle by 5 radians per, not second of course, in fact it cannot be 5 radians, bad example, so let us say by 10 degrees a second. You don't do that. Somebody asks you for ray, what do you say? Just go ahead, take the third right. You don't tell the person that move your knees like this. So I abstract that out. And the position and the orientation appears to be doing good enough for just encoding my motion, for encoding whatever changes in the environment, and practically, that's exactly how I'll move. Z again. Now I know that the IIIT Allahabad roads have a little hills and valleys. Not important. They change a little bit. When I move, I also go up, down, up, down. That's because of the biomechanism by which I walk. Not important. X, Y, and orientation is enough to really encode what my position at every point of time is. Now, some people do that a little bit more curiously. They say turning doesn't take effort. Humans can walk in any direction. So even if you need to move back, which rarely happens, people say that the turning back around is something that's not really widespread, and it's something that does not even take a lot of time. So they say that even orientation could be abstracted out, even though that's one of my favorite questions. Sometimes orientation cannot be abstracted out. You just have to take it because the cost, the motion cost, the definitions are too much into orientation. Like, if you turn, you can only move where you look at, and if you want to make a 45 or a 90 degree turn, there is a cost, and you cannot get rid of that cost. So you may not be able to abstract that out, but first example, easiest example, let's say that human being is what? In my case, a very big sphere, circle, still not a sphere, can move in almost any direction instantaneously, so doesn't matter where you're looking at. The small thing that orientation does is what we'll care about at lower levels of abstraction. What's left with is just your XY position in this beautiful image. Now, that's pretty interesting. There are two things that I did. One, why am I abstracting out details? What's the need? And the reason is that the lesser be the number of variables in my state encoding, the lesser will be the size of the state space, and the lesser is the size of the state space, the lesser my algorithms will have to invest on the search. Now there's another thing important, and mostly when things get regularized, people forget about it. I've abstracted out so many vital things: hip angle, joint angle, orientation. Now excuse me, your motion will be from 5-5 go to 6-5. In other words, walk 30 centimeters ahead. Now, you cannot walk 30 centimeters ahead. If it was a robot wouldn't have understood what is 30 centimeters ahead. Robots operate by physical motors. It's the same motors by which fans operate. And if you want to move a robot forward, you either have a library or you write that down yourself. So whatever has been abstracted out after the getting the solution might have to be abstracted in. I said the moving vehicles don't matter. Do they really not matter? No. Now, if I'm moving ahead and I have a car, I'll have to adapt my plan. So at that time, I'll have to abstract that in. I'll have to do something. My plans are not correct. I cannot blindly execute my plans. So the rationale for today's class is that leave in as many details as possible so that you end up in smaller problems which otherwise will be unsolvable. You make in most assumptions possible, otherwise you cannot even proceed. And that's what we are saying. We are saying assumption, 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 abstraction, abstraction, abstraction. Then I get what is called as a plan, or so-called as a path. So this gives me sequence of things I need to do. Walk here, then walk here, then walk here, then walk here, then walk here. Do the step, then do the step, then do the step, then do the step, and so on and so forth. And then I will execute the plan or the path. So all that I'll do is that I know step 1, step 2, step 3, what I need to do is I'll blindly do all the steps one after the other. However, now I'll have to cater to everything left out over there. So abstractions and assumptions. So what happens when the assumptions don't hold good? What happens if I'm at the wrong level of abstraction? So I said just go 30 centimeters ahead. And once I just said go 30 centimeters ahead, of course, there's nothing like that a system could potentially do because it's moved by motors. Then we say that this plan is solved as a weaker problem, as an easier problem by another algorithm, which of course for this specific case is called as the control algorithm, and that caters to all the abstractions and assumptions. So here we'll assume that all our abstractions and assumptions are valid, and we won't care about those hybridizations and how to inject the abstractions and assumptions in when you execute. which exactly is my specialization. For introductory course, we won't take care about that, but we may assume that the assumption and the abstraction, they most naturally hold. And therefore, every problem that we solve in as a part of today will be called as a toy problem. So it's just a toy because we're not looking at the real issues in reality. We're just making in assumptions which will not hold good. What happens when they don't hold good? Not a part of this course. So we're discussing some toy problems around. So now we know what a state really is. And because we know what a state really is, let me highlight that up a bit. And because we know what a state really is, what we now need to do is to see, can I abstract this more out? If I can abstract this out, believe me, I will be into a much, much better picture. So, I am a man who will always follow roads or pavements, and of course you know how does a road or pavement look like. It looks like this. Now, when I'm walking on this road or pavement, there's nothing around. Do my lateral movements really matter? No. I'll mostly follow the straight road in the middle. I've abstracted out anybody else who was moving vehicles. My lateral movements do not matter. My longitudinal movements do matter because I'll get closer and closer to my destination as I move along here. Even in case of the dimensions, the width of the roads is probably at IIIT Allahabad couple of meters. We've got narrow roads. However, the lengths of course are 500 meters, so they're really huge. And once you say that your length does not matter, your width matters, that means I can abstract this little thing by something which we have been doing into a lot of physics, which is to say that's the road, width doesn't matter. And if I apply the same principles around over here, I get in a much, so the abstracts, I've abstracted out the trees and everything, it wasn't important. Why do I even show it around over here? So I have a much more familiar picture around over here. So that's CC1, that's LT, this is of course CC2, this is the physical roundabout, and of course you've got some girls hostel here, you've got the admin building over here, you've got in the main gate over here, the auditorium over here. So that's actually the road network graph of IIIT Allahabad. The width of the roads absolutely did not matter. Now, interesting observation, assuming I start over at one of the intersections over here and I need to end at another intersection over here, if I'm standing around at any point, let us say around over here, I'll always take pedestrianized routes, motor routes, but I won't walk into the park. I can either go here or I can go here. There's nothing else which is possible. If I'm going here, I'll keep going here until I reach here, from where I'll get an options here or here. If I'm here, I'll take this or this, which means in the middle, where am I at the road is also not important. It's absolutely not important. I'll not go from the middle of the road back again. So if from here, if I started towards this place, I will end up taking this route in totality. Otherwise, I would have taken this route in totality. If I take a route, I take it in totality. So my information in the middle of the road is also immaterial. And therefore, I abstract out my positions also to just the intersection at which I am. And that's exactly what you do. Somebody asks you for a road. Somebody asks you, I want to go to the cafeteria. You just say, go ahead, take the third right, take the first left. Simple enough. That's how you guide in people.